Hello, everyone. Welcome to our second session of the beginner-friendly Transformer Architecture series. Before we get started, as usual, I want to give you a brief overview of the event series itself. So the goal of these talks is to help you understand the Transformer architecture more in depth and generally understand what it is. This event series consists of multiple events. So last week we had our first session, and today's is the second part, and it's called the Encoder-Decoder Pipeline Demystified. So this talk breaks down how the encoder and decoder interacts to process and generate language. So essentially the main topics that we'll cover today is understanding the encoder and decoder stack, and then step-by-step walkthrough and visualization of the flow. And please follow our social media and community platforms to be notified once we post new events here at algoframe.io. And again, we want today's session to be as interactive as possible. So feel free to drop any questions you have in the chat, and we'll be happy to answer them live. Now I want to introduce you to our special guest today, Navina, who is a senior AI and ML engineer at Bitstrap. So thank you so much for joining us. Please take it away.
All right. Thank you so much. Okay. So this is part 2 of our Transformer Architecture series. In the first part, we spoke about pre-transformer architectures and their limitations. We also did start with some very basic building blocks so that we're able to follow the math in the upcoming slides better. And yes, and then we had a top-down approach to the transformer architecture. This time we will look at each of those components in more detail and look at how the data flows through each component. So let's get started. Okay. So last time we actually drew each of these components here, and let's see how data flows through these. So the first component here is input embedding, and embeddings, as we discussed, they are numerical representations of a word. A word is actually broken down further into tokens. So tokens are like subwords. The idea there is, say you have a word running, and you break it down into run and ning. And so that way you can control the size of your vocabulary, because words will be broken down into their root or like root format. So that way we can control the vocabulary size a bit. But like embeddings are basically the numerical representation for words. And how are these generated? So embeddings are generated by embedding models. OpenAI, Google, all of them have their specific embedding models which can be reused. These models are more lightweight than LLMs. And so if we look at this vector here, it's three-dimensional, it has 3 elements. And in reality, we actually use, say, large embedding models with around 3K dimensions, and then smaller ones with around anything between 300 to 1500 dimensions. Okay, so these words are passed through an embedding model during training. And how are these embedding models trained? So they're trained using two techniques, like either you use a word to predict the surrounding or context words, and then the other which is called as skipgram, and then the other technique is you feed in a bunch of words together to predict the target word, which is referred to as continuous bag of words. And the idea here is that if the model learns to do this better with time, then it essentially is learning the numerical representations, how different words are tied together, how they appear in that n-dimensional space. And so this is about this first embedding model component, which is very critical. And so when these words, this is our input, hi, how are you, are passed through, there's a tokenizer that tokenizes these words, first of all, into tokens. Then we use a vocabulary that converts the tokens into token IDs. And then for those token IDs, we already have the embeddings which were learned. And that is how we get these embedding vectors. Now, as we move forward, let's keep in mind the colors that we see here. It's going to be useful as we go through all of these layers. So yeah, so we have these orange vectors with the embeddings being generated. And then next we have positional encoding, which is represented by this component here. So time step refers to the index of the words in the sequence, in the incoming sequence. These orange vectors is what we generated, the input embeddings. And positional encoding refers to encoding the order of these words. Now, why is this required? So first of all, say we take a simple, we take 2 3 words together, man eats pizza, versus if the order gets interchanged, it would become pizza eats man, and that completely changes the meaning. And so the order of the words is important. The other way to look at it is in our earlier techniques. So, in our part one, we covered the pre transformer architectures and a lot of building blocks, which are very important to continue with this session. So, if you've not seen it already, please do visit it. But there we covered how RNNs and LSTMs, these earlier architectures, they fed in the words sequentially. And so one word learns from the previous, which is fed into the next, and so on. But here we want to parallelize things. And so each word is learning about how much attention to pay to every other word. And this is happening in parallel. And so the order becomes very important. And how are these encodings generated? So in the original paper, attention is all you need. This was done using sine and cosine functions. So like this in itself is a deep topic, and so we will park it. But the intuition here is that you have a bunch of waves, sine waves for the even positions, and then cosine waves for these odd positions. And you have a bunch of waves being generated with different frequencies and wavelengths, and that is how you get each element for this positional encoding. And that you sum it up with the original embedding element by element, and that gives you your positional input embeddings.
Mhm. Interesting. Just we'll pause for a couple of questions. So, firstly, how important is the choice of the embedding model, I guess, and how do you choose one? Because, as you said, there are a lot of different ones. So, are there any criteria or any, I guess, specifications that developers, right, or ML engineers need to look for when choosing an embedding model?
Yeah, so it depends on, you can say, nuances. If these if it's a general use
Mhm.
case, the pre-trained embedding models out
Mhm.
there suffice because they've already been trained over a large
Yeah.
vocabulary. If you have something very specific to your use case, you might want to fine tune.
Mhm.
And additionally, it also depends on how lightweight is your use case.
Mhm.
So if it is lightweight, you could use like a smaller embedding model which has limited parameters, so then you're optimizing for latency, and then the costs incurred.
Yeah.
But otherwise, you could go in for like a large model.
Mhm. So, and what about other languages? So, are those general embedding models or also sufficient for, like, let's say Chinese or something like that, or it would also need to be fine-tuned, or yeah,
Yeah, I think we have specific models per language.
interesting. And
Yeah.
then the second quick question is, so is positional encoding done by the embedding model itself, or it's completely different like function that runs as part of this pipeline?
Yes, so this is a separate block that we see
Okay,
here.
okay. Awesome. Perfect. I think we can continue. Thank you.
Thank you. Okay. So to continue, we have positional input embeddings now generated. And then we look at this next block, which consists of the multi-headed attention and feed forward. So multi-headed attention is like the main feature of the transformer architecture along with the parallelization that it provided. It's actually inspired by how our brains work as well. So if I am given a para, I will subconsciously focus on certain key words or concepts, quickly extract them, and this is so subconscious and like paying attention to certain words. And so then, how do you do this in this architecture mathematically? So the idea here is you feed in these embeddings, and at the end of it, you get the attention encoded representations. And so let's look at what's happening here. So self attention, it is a function of query, key, and value. And there is this equation. And then how is this implementation, how is this equation actually implemented? So like it says query into k raised to t, which is transpose of this query vector. So what is transpose? So transpose is an operation that flips the orientation of your matrix or vector. So like in this case, if it is a column vector, it will be flipped to, so like if your keys were like column vectors, if you apply a transform, they will be flipped to such row vectors. And if we look at the operations first, you have say for each word, hi, how are you, you generated query, key, and value. So then this operation q into k raised to t is like your first matrix multiplication that is being covered here. And we will move further on. But before that, let's take a look at how these query, key, and values will look like. So this is our positionally encoded embeddings. These are our positionally encoded embeddings. Hi, for hi, how are you? And we could multiply them by some other matrix to generate the query for hi, the query key and value vectors for hi itself, and then similarly for all the others from their base vector. To simplify this, here we are just say multiplying each of the elements here by 2. So you multiply by 2 and you now have a new vector, query vector for hi, and maybe you multiply by 1 here, so you have a key vector and a value vector here by multiplying by 0.5. And why are we doing all this, right? Let's take one more step back. Why are we doing all this? So this is actually inspired by information retrieval systems. Suppose I put in a query into Google search. And so my query will be converted into embeddings. And the documents are also indexed. And the embeddings are stored on the Google server. And they will be matched. So there will be similarity algorithms or scores that will be generated. And that is how, when I query on Google, I will get my top retrieved ranked results. And so there you have a query and a document embedding. Here we are talking about query and key, and then an associated value embedding. Okay, so now with this context, let's go back.
And just to clarify, so essentially, like in simple words, key, value, and query are essentially are created from the input embedding, right? Like with some kind of formula, right? And as you said, like key value and query are used in different use cases, right? Whenever you build a certain feature, is that correct?
Yes, so they're derived from the base vector
Mhm.
itself, and the idea is they will be used further for the attention score generation.
Awesome. Cool.
Okay. So now we have the key transposed here, and we have these query vectors. They will be multiplied to generate scores. And again, going back, so this is how the multiplication looks like. So query for high multiplied by key vector for high, and this is the matrix multiplication. This is also the dot product. So 2 into 0 plus 4 into 0 plus 8 into 2, and that's how you get 16, which is placed here. So this is how much attention high will pay to high. And similarly, high and how much similar are they? This can be computed similarly by multiplying this by this, and you get 12 here. And this way we have these attention scores. So we have a bunch of similarity metrics. There is dot product, and we will not be able to, perhaps we could cover this towards the end, but like we have a bunch of metrics, Euclidean, Manhattan. So these are distance metrics, and the like one minus these will give you similarity. But overall, based on the number of operations involved, dot product is the most computationally efficient, and that's why it's used a lot in transformers, in neural nets. Um, so this operation that we were looking at, like just multiplying, this is something we actually started off with in our last session. So if we look at we started off with this linear equation wherein y is a function of x, and we've referred to this as the weighted sum of the inputs, because you have the input features and you have weights attached to them. But if we extract these x's here and place them like this in a vector, and similarly the w's are extracted and placed like that in a vector, and then you multiply them, this is referred to as x dot w. This is the dot product, this is the sum of the product of corresponding elements, and this operation is used a lot. We'll be using this throughout today. So we were looking at this part here, and we have the scores now. So let's go back to our yeah, we have the scores here, attention scores. One thing to observe is that the scores will be the highest diagonally, and that is because each word will be most similar to itself. So like high is most similar to itself, how will have the highest score for itself, and so on. And then some scores for the rest of the words in your input as well.
Just a quick question. Like on this diagram, you have query and key, and they get multiplied to get a score. And does the value play a role in here? Because in the formula itself, you take it as an input, or yeah, but on the diagram it's not there. So
Yeah, so that will follow.
okay, that's
Like
good.
so we're at, so good observation. We have just multiplied the query and keys here so far, and we will start
Oh,
using
okay,
their
okay.
corresponding values
So just
above.
the first step. The first step. Okay, cool. Yeah.
Yeah, we are here. And then moving on, we scale these scores that we receive using the dimension of the key vector, square root of the dimension. And this is again done simply to stabilize the training, not have too high values, too large values involved. So like curtailing them, having them restrained, and so we get scaled scores next. And Again, this is something we touched upon in our last video, if you would like to revisit it. And but with this, we're done with scaling. And then the next operation is softmax. So softmax is another activation function, and the equation is here. It basically is used for um, multi-class outputs, like where you have multiple words or like multiple classes from your neural nets that have to be outputted. Um, and the benefit of using softmax is that it returns your probability distribution over each of your words. So like each word's output will be between 0 and 1, and their sum will be 1, because probabilities at max can be 1. So like we see here, this will sum up to 1, and the next one will sum up to 1, and so on. And the advantage of this is, if you see, um, the diagonal elements here had the highest value, and that is maintained. So the high values, it is like amplifies them further, and the lower values, it diminishes. And then now we have the values getting involved, this value vector. Now this itself is it took me quite a while to myself like understand what's going on here. It's quite deep, so let's take a look at it. It's not like our normal matrix multiplication, wherein you have, say, a 4 by 4 matrix, and these are vectors, these are not even matrices. So this is not like 4 by 4 into 3 by 4, 3 rows and 4 columns, and then you get your output. So let's take a look at what's happening here. So these were the scaled attention scores. These are the value vectors. Now, if I want the attention encoded vector for the word high, I will first look at high's attention to, say, the first word, higher. That value 4 will be used to scale the corresponding value vector. So 4 into 2, 8. 4 into 1 is 4. 4 into 0 is 0. And so we got the scaled value vector. So, and then similarly for the next word, how. High's attention to how is 1. And then you multiply 1 with each element here. So you get back the same values for how. And similarly for R and U by multiplying by 0 and 2 respectively. And then you add these up. So 8 plus 1 plus 0 plus 2 is equal to 11. And that becomes your first element. And similarly, you add for the next elements and you get your attention encoded vector for high populated here. So why are we doing this? So like the idea here is you want to pay attention to every other word, but in varying proportions. And how will you decide on how much to uh, pay attention to each individual word? That will be based on the similarity with that word. So like high is most similar to itself, so you have a higher weight while multiplying, and as you see, that reflects finally also this 8 will contribute the most in the attention scores for high. And so this is very deep. Maybe this could be revisited later to get like a better understanding. But this is how we finally, for each word, now we have vectors with attention also encoded. And any questions on this, Alex?
Yeah, I think, as you said, there is a lot of math here, but I think the way you explained it generally makes sense. So,
Sure.
essentially, it's like this: the input, right, is this. So attention weights, which is the matrix, then value is the embeddings, right, and then you also get embeddings as a result. In a nutshell, correct?
Yeah, like attention weights by that key and query
Yeah.
multiplication, which will give similarities.
Uh-huh.
And then based on the similarities, you scale the corresponding values. So you're considering each value, but you're scaling it based on its similarity.
Mhm. Maybe a
Pretty.
question is how did people come up with this math? Like, is that essentially years of research, mathematical research to like to come up with this formula? Or yeah, how was it initially created?
Yeah, I think the dot product that we do and all of this matrix multiplication is used a lot in for like scaling these models. But I think this intuition is, as we were talking last time, it was like attention mechanism came into picture in 2014, but like using it with encoder-decoder style is what was introduced by that paper, Attention is All You Need. And that revolutionized AI because you can actually do these things in parallel, right? What we just explained for high, it could actually be done for so many inputs together.
Yeah. Interesting. Awesome.
Okay.
Yeah, let's continue, and then yeah, if there are any questions, I'll let you know.
Okay, thank you. So yeah, so now we get a better idea of this looks a little vague without the numbers, but like what is happening, the math here, we've kind of explained that. And this is my one liner to like summarize this. So like the new self attention values for each token contains input from all other tokens, but relative to their similarity to the word for whom attention is to be established. Okay, pretty deep, but we when we revisit this, maybe it'll make more sense. So we started off with query key values and we fed it into an attention head. We got these attention encoded vectors for each word in the input. And now these attention heads, like you could have multiple such heads, right? So like we generated some random query key value vectors and you could use some other um, multiplication to generate another set of query key values. And so that way you're now learning different nuances from your input and paying attention to different aspects. So that covers the attention heads. And so these are like three element vectors and we stack them up. So like um, the vectors for high will be stacked together and so on. And then you just run it with a linear network that we covered during our neural nets at the start in video one. So the idea here is you again want to pay and attend, like you want to learn from different representations in different quantities. And so like this will be learned, you could add weights attached, how much to consider each of these, and that way you have your multi-headed attention. Now moving on to this arrow that we see here, so it's referred to as your residual connection. So what we're doing here is the positionally encoded embeddings that we're generated, we're passing them also forward by a separate path, so that way they do not get diminished as they pass through this layer. That's one way of looking at it. And this component itself can focus solely on the attention generating bit, attention encoding bit. So this is referred to as residual connection. After that, we see add and normalization. So that is shown here. So these orange vectors plus these green ones, we add them and then we do a layer normalization. So again, normalization refers to limiting the range of your inputs. So if it was like you have numbers from 0 to 1000, maybe you just divide them by 1000. And so then you get numbers between 0 to 1. And if you run this on the inputs to each layer, that is referred to as layer normalization. So it helps in more stable gradients, better learning, lesser training time, and lesser fluctuations during learning. And these will also be passed directly forward using a residual connection. And you will also pass these via our standard feed forward, which is common for neural nets. And so you will see a bunch of linear and non-linear layers in the feed forward part. And finally, we add an so we add these two components and we run layer normalization. And with this, you will, at the end of this, as we see, like we are going to be doing a sum of these two vectors. So we finally will have a single vector for each word. Hi, how are you? Which is shown here. And so, as we see, it has actually encoded so many things: orders, numerical representations, attention weights, multiple nuances in those attention weights, and how much to weigh them using weights and biases. And now these will get fed into the
Decoder.
decoder block.
Mhm.
And modern LLMs, sorry, were you saying something, Alex?
Yeah, I was going to ask a question, but finish your thought and then, yeah.
Sure. So modern day LLMs, they are decoder only, which means they take this input, the embeddings, and because they are trained on so much data and compute, and they're really large in terms of their parameters, they're just able to learn with this embeddings directly that have been generated, input embeddings. But encoder decoder could have been used together, and it would have added latencies though. And yeah, so please go ahead, Alex.
Yeah, thank you so much for the detailed overview. Yeah, as you mentioned, there are a lot of like mathematical computations there. I think just maybe a couple of quick questions. So, about those attention heads, right? You call them. So, like, why? And then on your diagram, you had two of them, and then they would be like kind of merged together. So, like, why do you need two? Where like kind of why isn't one sufficient? Do we need like maybe more than two? So that is one of the questions.
Great question. So it's like, even when I'm paying attention as a human, I might be paying attention with regards to different categories, right?
Mm.
Like maybe subconsciously, when I'm paying attention, on the one hand, I'm looking for certain very unique terms. And so that catches me, stays, retains in my memory. And then I might be paying attention to like different components of a text para that I'm reading, but like how do I link them? So paying attention to that link. A third attention might maybe be focused on the concepts itself. A fourth attention might be focused on the grammar. And so you have a lot of nuances, and you want to capture all of them, you want to build on top of all of them, and like how much attention should I pay to each of these? Like which head
Yeah,
should
yeah.
I pay more attention to? So that can be learned. And so that's the idea of having multiple attention heads.
Interesting. Okay. So essentially it depends on your use case then, right? So the quantity depends on your use case and how in depth you want this encoding to be, right?
So these LLMs that we use, they're pre-trained. The exact number of encoder and decoder blocks in them, subtle variations in their architectures are often not published.
Okay.
We do know about the parameters overall,
Mm-hmm.
but yeah. So in that case, like they are generalized. They're trained in such a way that they should be able to meet most of the requirements, most of the
Interesting.
requirements in general. And then maybe for math or for a physics problem, sometimes now you have more distilled models that just are like smaller, lightweight variations of your
Mhm.
main model. And so there maybe you could have these specific attention heads based on what you
Yeah,
want to.
makes sense, makes sense. And one other quick question, I think it's more for our beginner audience. Just to clarify the terminology, so like vectors versus embeddings, when would you like call what? Because I think I call everything embeddings and I don't think it's right. So it's like, yeah, when would you essentially embedding is like the input, like the initial input, and then vector is like a product of whatever mathematical operations you do on those embeddings, initial embeddings.
So words are represented by their embeddings.
Okay.
The embeddings are numerical representations. So now how do you store those numerical representations? So if we think in terms of data structures, should it be like a dictionary or should it be like a tuple or so? It should basically be like an array containing those numerical representations.
Yep.
But then here we are using vectors. So
Mhm.
embeddings, when we say embeddings, it's actually embedding vectors.
Oh, okay. Wonderful. So can you use those words interchangeably though, then, or?
They do refer to the same thing. It's just
Okay.
that one speaks about more of the about like the meaning, and then the other one is capturing the structure involved as well. Because we these are not looked at in isolation, even while using and even while training. So it's always about this numerical representation, and then how it in that huge vector space, how does it interact with the other words, what are the
Mhm.
similarities. So that's why vectors become important.
Okay, okay. Awesome. Yeah, thank you for clarifying that.
All
Cool. Let's move to our second part, decoder, and
yes,
yeah, so
sure. So here we start with start of sequence, the default word with the inputs, and it'll generate the first word I. This will be fed back in, and then you'll have the next word coming up, being outputted by the decoder, which is am, and so on and so forth, until finally your last word is fed in, and the decoder generates an end of sequence token. And we see two new words here: forced training along with autoregression. So this means that while training, even if the decoder were to go ahead and generate like a longer sequence, because it's still learning, it's making mistakes, if you have ground truths that are provided and there you see this end of sequence, it will stop. So like you'll force your training to stop. So it's like forced training, teacher training. um, and then auto regression simply refers to regression because you're generating one probability value the from other values, and auto regression because you're doing this based on previous words that it saw. So previous outputs generated by itself leading to each of these newer next words, and so auto regression. And the initial layers here will be the same. So output embedding, positional encoding. um, this is interesting. Here we are saying that when we're generating the attention scores, each word should learn like should be able to pay attention to what it has seen so far. So like it should be able to attach a weight to itself and the words previous to it, but not the words which will follow. So if we allow it to learn from scores that are going to follow, then you're essentially like um, you're leaking data during training. That should not be allowed. And so like am can attach weight to start, I, and itself, and find the final word can add weights to all the words prior to it. And this upper triangle of this matrix should get masked. So in order to do that masking, we will have this look ahead mask with 0 and minus infinity values. And when we sum each element of these two matrices, um, wherever we see zeros, which is the lower triangle here, those values will remain as is. And then for the above ones, 0.1 plus minus infinity will stay minus infinity. So that way we still have these showing here. And when softmax, which is our next component here, is applied to this masked output, because of the equation of softmax, we end up getting zeros for where we saw minus infinity, and the sum of all of these will be 1, because that's the property of softmax. And so now we have our attention scores, and in this case also the diagonal elements will have the highest values, and cross attention. So we saw attention heads in the encoder side to know how much attention should each input word pay to every other input word. We saw attention heads on the output side in order to know how much out how much should each output word pay attention to the output words it saw before it. But we would also want that my output that is generated by the LLM should be relevant. And for that, it needs to understand the relation with the input context also, right? And that is how these LLMs are doing so well, because they're really able to understand the context, input context that we provide them. And that is managed by cross attention. So here, the key vector will be of the output word, and because that's like your the query vector will be of the output word, and the key and value vectors like the similarity scores will be against the key and value vectors coming from the input side. And so this is referred to as cross attention.
Maybe a quick question. You mentioned like context generally, like those that LLMs like take into account the general context. But like for example, right, with ChatGPT, let's say, I know that it essentially has context over all of the chats throughout like a very long period of time. So how can you provide so much context into this? Like, doesn't make sense. It's like thousands of chats, and like how can you feed all of this into one simple context, I guess.
Amazing. So that's a great question, and that takes us back to our some parts of our video one. So you asked two parts. One is the immediate context that is being fed
Yeah.
in a way that is like short term, like that is your short term context. And then you have things that were from your prior chats that have been moved into memory, persisted memory, either vector DB in say, or like Redis cache, um, memory store, and so that needs to be fetched as well. But you don't want to fetch the whole thing. You want to fetch only some part of it which is relevant here. So how will you decide on the relevancy? It will be based on, again, the similarity of the embeddings of your question to the embeddings which are stored in memory. So there in memory you might have a lot of embeddings, but some of them might match and be more relevant to what you are asking. So that will be fetched, and that is what we do in RAG as well. Retrieval augmented generation. And so like retrieval, so it all ties to information retrieval that we were talking about earlier. Like you have embedding stored and you have a query embedding, matching them, picking up only certain parts, and that is how you have both your previous chat context and your current context being fed in. And about the window, so attention mechanism could hypothetically have an infinite reference window we were looking at earlier, because of this attention mechanism which can compute these attentions in parallel. So you're not passing this whole input one after the other, which is leading to losses which we saw earlier. And so that's the advantage, because you're not doing these long term and short term paths. Does that answer your question?
Yeah, I would say it does. So essentially, as you said, it's like it does this RAG search, right, on your previous chats, right? So it looks as you essentially kind of summarizing your response, and correct me if I did if I'm wrong, but essentially all the previous chats are stored as vector embeddings in long-term memory, right? So in a database, let's say, and then whenever you do a another query in a different chat, it will actually, as part of this entire process, it would also go look up if there are any similar chats that you've had before that relate to your current conversation. And if yes, then it pulls it and also feeds it as a additional context. Correct? Okay.
Yes.
Awesome.
Yes.
Perfect.
Amazing.
Maybe where does this happen though? Like in this diagram, like where is this step happening? Is this like at the very beginning essentially, or it's somewhere in the middle?
Good question. Um, that step of all the context being fed
Yeah.
in is not shown here because we're only talking about what happens once the context is made
Yeah.
available. But to your question, you can think of these orange vectors here, which represent the input embedding
Hmm.
vectors. You can think of this as being a combination of the query, like, and the prompt,
Yeah.
and the prompt could consist of that long context as well.
I see. I see. Okay, makes sense.
Yeah, so that will be used to generate your first word, and then keep continuing that sequence so that it is very logical. And yeah.
Perfect. Okay. Awesome. Yeah. Let's move on to the next part. Thank you so much for
Sure.
answering the questions.
Yes, absolutely. So yeah, now we're almost nearing the end of encoder decoder pipeline. So we have these few components here, which are very typical in neural nets, and we covered them earlier as well. So um, multi-headed attention, feed forward network. So you have a bunch of stacked neural net layers, and then you have a linear or like a fully connected layer, which will give you which will have like one neuron per uh, output word. So like the output words that could be generated will be equal to the vocab size, right? Like I have a vocabulary and I output the most probable next token from that, but representing each of those vocab words as like one class. So this becomes like a multi-class problem, and representing each of them by like a neuron, which gives a score, a raw score for each of them. And these are also referred to as logits, logots, and there's a little bit of math behind it, but in the interest of time, we will skip that. But this layer has some math, and let's think of it as raw scores that can be between minus infinity to infinity. And then we apply softmax, which is used often in multi-class classification as the final activation function. And that, as we saw, it will give you a probability distribution over all of these words. So it will give you a probability for each of those words, each of those classes, each of those words in your vocabulary. And the sum of these will be 1. And then the most likely word is picked up, the word with the highest probability value, and that is what is outputted. So here we have output probabilities. And okay, so like we were referring to earlier about learning from different components and units, stacking them up, one encoder will consist of one feed forward network, and it could itself have multi-headed attention. And the output from that encoder, as we saw, are those vector representations for each word. Now, those itself could be fed to the next encoder layer. Because to this first layer, where did we start off with, right? We fed some embeddings, some vectors for each word. And now that initial embeddings, we refined it, added more features to it, but our output is still like one vector per word. And so now that richer representation, you pass it even further to the next encoder block to learn more complex features and relationships. And like this, you could stack multiple encoders. And the output from that final encoder could be passed to your decoder unit, which itself, like, this is one decoder unit, but you could stack them up and learn different aspects even there. And this is about our encoder-decoder pipeline. So we walked through it with the math, the vectors involved, how actually the vectors flow through. Like, these were just blocks,
Mhm.
but like really understanding how these vectors flow through.
Okay, that's awesome. Thank you. Thank you so much, Navina, for this detailed walkthrough. Um, I think a couple of quick questions. So I remember, or if I recall correctly, you mentioned that sometimes, right, encoder part can be dropped, right? So essentially the question would be, like, can you just remind, like, in what cases that happens? And then if you drop, like, essentially the main goal of the encoder, right, is to put together all of the context, all of the, I guess, those formulate the most efficient vectors that can be fed into decoder to create, like, useful outputs. But, like, yeah, in what cases would you drop encoder? And if you drop it, what would be the input into decoder then?
Yes, great question. So, encoder and decoder blocks, let's understand the roles they play. So, encoder block, it takes in some input of words, and like those words are fed in using their base embeddings, and then it generates a vector representation for each of those
Mhm.
words, like we saw here.
Yeah. Mhm.
And so this is the output from your encoder block. And the purpose of decoder is to learn from these
Mhm.
features and generate an output given these
Mhm.
features. Now, encoder decoder together would mean you would always have to use the encoder block also. So there is more training involved, far more parameters, and even during inferencing, then there will be more latency, more computations to run,
Mhm.
and so it will not be as computationally efficient.
Mhm.
So what is done instead is only the decoder block is used,
Mhm.
and instead of feeding these, because now there is no encoder to encode
Yeah.
information, directly the base
So
embeddings
the raw embeddings, the
embedded
initial ones. Mhm.
are fed in.
Okay.
And if you think about it, those embeddings which we were covering about here,
Mhm.
they are themselves coming from an uh, input embedding part, which is an encoder only part.
Mhm.
So, in a way, you do have that encoder only part coming into the picture, but we're not explicitly adding all these encoder components that we saw here. Um, so, we're not running through these, we're just passing the base embeddings directly
Mhm.
into the transformer decoder. And because these LLMs, they're trained on so much massive data, and they require so much memory and compute. They're trained on such a wide range of resources. They're still able to learn
I see. I see.
just from the base embeddings, and so it is very powerful what we're doing here.
Okay. Okay. Sounds good.
So the idea is, like, with more data and with more yeah, running more training, you can actually scale these models, like, by adding so many parameters that you need to learn, so many complex relationships. You start off simple, but it's still able to learn because the training itself takes like a few days.
Mhm. So are you saying that essentially encoder can be used during the training stage, and then when you actually go into production, that part can be dropped? Is that it's not very accurate?
So encoders are used for generating the
Mhm.
embeddings. So they're embedding models
Yep.
those embedding models which are meant to like output the learned representation vector embeddings of each word, their encoder only architecture is used. And then that layer is during training, you could train them together, like the input embedding, you could train it at that point. Typically it's reused, and then the actual decoder layers are trained. And we were talking about languages earlier, so similarly it's about like how do we model some of these things. So like per model you have, sorry, per language you have these embedding models. That is how it was done earlier. Now you also have multilingual embedding models. So they just take the embeddings from these different languages and put them into a joint space. So like then you have embeddings from different languages being put into a common vector dimensional space, and you keep learning.
That's
Like
crazy.
the idea is with enough data and with enough memory and compute to process that data, you can learn so much with this architecture because of the parallelization that it offers.
Yeah.
And keep pumping in more data, and we're seeing the results. Like we started off with these GPT-2 models, etc. Maybe they were like a million parameters, and now you keep feeding in more data. You're running them with so much GPU attached, TPUs in case of Google. So then they're able to scale. They're just getting better and better and better.
Yeah, that's awesome. Also, another final question is where does so decoder? Excuse my like simple language here, but where is the actual thinking process happen? Where does it actually happen? Because like it's in decoder, I assume somewhere, right? Because like again, encoder it just processes the input, and then decoder would be the actual part that because like when I feed something to ChatGPT, right, it doesn't give me the same thing back. It gives me like a certain like the actual answer to my question. So like in this, as part of this, like what component is responsible for like the actual thinking process?
Great question again. So different decoder blocks that are stacked, they will in a way contribute to different features. They will lead to different so it's you're thinking in a way by those different units. Each of them is being used differently. The other way to think about it is we also know that the model can get really creative by certain hyperparameters like temperature, right? So when we increase the temperature, the model gets creative. And so what that does is it does not just consider the word with the highest probability, it considers a bunch of words based on yeah, like a limit that you'll define, like choose from the top X words or choose from this part of that probability distribution. And so that way you get creative. That's one thing. And about reasoning itself and like thinking, you also have these mixture of experts models, wherein you have you're able to optimize because you have different like you still have those many parameters and weights involved, but at different points you will have different parts of your network turned off by those activation functions that we were seeing earlier. So based on your problem, you will activate only certain parts. And if you need more complex reasoning, research related problems, it will take up more budget and cost, but it will involve uh, activating those parts.
So this like research mode in ChatGPT, essentially, it activates more like layers, I guess, that the input goes through to like provide a more comprehensive output, essentially.
Specific layers, and then it has also already learned, like for research mode, it has also been fed in a lot of research data, so it knows how to process those type of inputs. And yeah, I was adding something, but yeah.
Sorry. Yeah, but that's interesting. That's interesting. Awesome. And maybe just something like as a final
Yeah.
closing note, what do you think would be the great next steps like for our audience here and generally for people who are watching later to, yeah, what would be the good next steps for them to follow, go through?
Yeah, just one more thought on the reasoning bit. That is where it's getting more and more advanced, even with agents that are able to like take an LLM output, but like refine it iteratively. So, like maybe you have another LLM that looks at the output from the first one and then decides if it needs further fine tuning, is it missing some logic, reasoning,
Mhm.
and so that way you're able to like generate more deeper output. And yeah, as next steps, I would maybe as a first step, I would suggest you look at my video one. And yeah, there are some references here at the bottom. So the colorful diagrams that we saw for the pre-transformer architecture, they are from this video one. And then whatever we walked through today are from this
Mhm.
video, essentially. But I've added more intuitive, like the math there.
Mhm.
So those could be great steps in yeah, we could probably let me know in fact what would y'all like to discuss further, and we can actually cover that.
Yeah, yeah, that would be awesome. Yeah, we'll really appreciate all the feedback that you can share with us, whoever's watching. So, thank you, but thank you so much, Navina. Really appreciate the content and the walkthrough, and thank you so much for putting all of this together. Thank you to everyone who joined us, and yeah, looking forward to seeing you at some future events as well. So again, please don't forget to subscribe to our social media platforms to be notified whenever we post another event. But yeah, thank you so much.